For decades, scientists told us the same story about the beginning. After the Big Bang, the universe was a hot, featureless fog. Gravity worked slowly. The first structures were small, fragile, and clumsy. Galaxies needed billions of years to mature. That was the story. It was clean. It was comfortable. And the James Webb Space Telescope keeps making it look wrong. Not once. Not as a fluke. Again and again, Webb peers into the earliest epochs of cosmic history and finds structures that appear too developed, too organized, too grown up for their age. Massive galaxies that should not exist yet. Black holes too heavy for their era. Spiral arms, chemical enrichment, and even death arriving billions of years ahead of schedule. The early universe is not matching the story we told about it. And the mismatch is getting worse. If you find this kind of deep science genuinely worth your time, a like or subscribe goes a long way toward helping us keep making it. We do not chase trends. We chase what actually matters. Are you comfortable? Now, let's begin. There is a version of the beginning that almost everyone has heard. You may not remember where you first encountered it. Maybe a classroom, maybe a documentary late at night, maybe a poster on the wall of a science museum when you were too young to read all the words. But the broad shape of the story settled into your mind at some point, and it has been sitting there ever since, unquestioned, like a piece of furniture you stopped noticing a long time ago. The story goes like this. Approximately 13.8 billion years ago, everything that exists was compressed into a state so small, so hot, and so dense that the word point barely does it justice. There was no space outside of it. There was no time before it. There was no before at all. The universe did not explode into something. It became something. Space itself began expanding, carrying energy and matter outward with it in every direction simultaneously. That first moment, that eruption of existence from nothing we can describe with current physics, is what most people call the Big Bang. Within the first few minutes, the temperature dropped enough for the simplest atomic nuclei to form. Hydrogen, helium, trace amounts of lithium. That was all. No carbon, no oxygen, no iron, no silicon, nothing remotely complex. The universe was a blinding fog of plasma, a soup of charged particles so hot and so dense that light could not travel through it. Photons scattered off free electrons in every direction. The cosmos was opaque. If you had been there, which is physically meaningless but useful as an image, you would have seen nothing. Not darkness, not light, just a white-hot wall in every direction with no structure, no contrast, no shape at all. This fog persisted for roughly 380,000 years. That is not a guess. It is one of the most precisely known numbers in all of cosmology. At that moment, the universe cooled enough for electrons to bind to nuclei for the first time, forming stable atoms. The fog cleared. Light was free to travel. And it did, streaming outward from every point in the cosmos, filling space with radiation that has been cooling and stretching ever since. That ancient light is still here. It arrives at Earth from every direction in the sky, not as visible light, not anymore, but as faint microwave radiation, cooled by 13.8 billion years of cosmic expansion to a temperature of roughly 2.7 degrees above absolute zero. It was discovered almost by accident. In 1965, two radio astronomers working at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were testing a large horn-shaped antenna designed for satellite communication. They kept picking up a faint, persistent hiss that would not go away no matter where they pointed the instrument. They cleaned the antenna, they removed a nest of pigeons living inside it. They rechecked every cable and connection. The hiss remained. It was the same temperature in every direction. It had no source. It was everywhere. What they had found, without initially understanding it, was the afterglow of creation itself. The cosmic microwave background radiation. The oldest light in the universe. A relic of the moment when the fog cleared and the cosmos became transparent for the first time. That discovery changed everything. It was not just a confirmation that the Big Bang had happened. It was a photograph. A baby picture of the entire observable universe taken when it was less than 400,000 years old. And when scientists mapped it in detail, first with the COBE satellite in 1989, then with the WMAP satellite in 2001, and finally with the European Space Agency's Planck satellite in 2009, the picture that emerged was staggering in its simplicity. The early universe was almost perfectly uniform. The temperature of the background radiation was the same in every direction, to within 1 part in 100,000. That uniformity told scientists something profound. At the moment the fog cleared, the cosmos was smooth. There were no galaxies, no stars, no planets, no structures of any kind. Just a faintly rippling sea of gas, nearly identical everywhere, with only the tiniest variations in density. Variations so small, they would be invisible to anything less precise than a space-based observatory. Those tiny ripples were the seeds. Not yet galaxies, not even the ghosts of galaxies, just places where the density of matter was fractionally higher than the average. Fractionally. 1 part in 100,000 higher. Almost nothing. But gravity is patient, and over hundreds of millions of years, those almost nothing differences would slowly, methodically pull surrounding matter toward themselves. Denser regions would grow denser. Less dense regions would empty out. Structure would emerge, not in a flash, not in a burst, but through the quiet, grinding accumulation of mass under gravity across enormous stretches of time. But first, the universe had to endure something it had never experienced before, and would never experience again. Darkness. Total, absolute, unbroken darkness. After the fog cleared and the background radiation streamed outward, the cosmos entered a period that astronomers call, without irony, the Dark Ages. The name is precise. The ancient light from the fog was stretching into longer and longer wavelengths as space expanded, fading from visible glow into infrared, then into microwave radiation that no eye could see, and nothing else was shining. The first generation of atoms, hydrogen and helium, drifted through an expanding void without emitting any significant light of their own. No stars had formed, no nuclear fires burned anywhere. The universe was a vast, cooling, silent expanse of gas, illuminated by nothing. This era lasted roughly 100 to 200 million years. That number is hard to feel in any meaningful way. The entire recorded history of human civilization fits into roughly 10,000 years. The Dark Ages lasted 10,000 times longer than that. And during all of it, nothing happened that would produce a single photon of visible light anywhere in the observable universe. The cosmos was not just dark, it was the most completely lightless place that has ever existed, or ever will exist. A void so total that the word dark barely captures it. There was no contrast, no shadow, no horizon, just hydrogen and helium, expanding and cooling, drifting toward the places where gravity would eventually call them together. And then, somewhere in that darkness, the first star ignited. We do not know exactly when. We do not know exactly where. The event has never been directly observed, but theoretical models describe what must have happened with considerable confidence. In the densest of those early dark matter pockets, ordinary gas had been slowly accumulating for tens of millions of years, falling inward under gravity, compressing, heating. Without heavy elements to help the gas cool efficiently, the collapse proceeded differently from anything in the modern universe. The gas clouds were enormous, the collapsing cores were hotter, and when the temperature and pressure finally reached the threshold for nuclear fusion, the objects that ignited were unlike any star that exists today. These were the population 3 stars, the first generation. Theoretical models predict they were immense, perhaps hundreds of times more massive than our Sun, possibly even 1,000 times more massive in the most extreme cases. They burned at temperatures and luminosities that dwarf anything in the contemporary cosmos. Their surfaces blazed with ultraviolet radiation so intense that it began tearing apart the neutral hydrogen atoms in the surrounding gas, creating expanding bubbles of ionized plasma around each star. This process, called reionization, would eventually transform the entire universe from a neutral fog back into an ionized plasma, but it took hundreds of millions of years to complete. The population 3 stars were also extraordinarily short-lived. A star 100 times the mass of our Sun does not burn 100 times longer. It burns millions of times faster. These first stellar giants exhausted their hydrogen fuel in just a few million years, then collapsed in catastrophic explosions, supernovae so powerful that some of them may have obliterated the star entirely, leaving no remnant behind. Others may have collapsed directly into black holes, and all of them, in their death throes, scattered the first heavy elements into the surrounding gas: carbon, oxygen, silicon, iron. The raw materials for everything that would follow, including eventually planets and the chemistry of life. Those heavy elements were the universe's first real currency of complexity. Without them, gas cannot cool efficiently. Without efficient cooling, gas cannot collapse into the smaller, denser, more varied structures that produce the second and third generation of stars. The death of each population 3 star was simultaneously a catastrophe and a gift, destroying itself while seeding the cosmos with the ingredients for a richer future. This is the heart of what cosmologists call the hierarchical model of structure formation. It is one of the most important ideas in all of modern astrophysics, and for decades, it held together beautifully. The basic logic runs like this. Small things form first. The first structures to collapse under their own gravity in the young universe were not galaxies. They were tiny clumps of dark matter, an invisible substance that makes up roughly 85% of all the matter in the cosmos. Dark matter does not emit light. It does not absorb light. It does not interact with ordinary matter through anything except gravity. But it was there from the beginning, and it clumped together faster than ordinary hydrogen and helium, because it was not affected by the pressure of radiation in the early universe the way normal matter was. These first dark matter clumps were small, perhaps a few million times the mass of our Sun at most. Ordinary gas fell into them, drawn by their gravity, and began to accumulate at the centers of these dark matter pockets. The first stars formed inside these structures. They lived, died, enriched the gas, and gave way to successive generations. Each cycle added complexity. Each generation seeded the next. And through this slow recycling, The chemical diversity of the cosmos gradually increased over hundreds of millions of years. Meanwhile, the small dark matter structures were merging. Two small clumps would fall toward each other, combine, and form a larger clump. 3 would become 1. 10 would merge over time into something more massive. And as the dark matter scaffolding grew, the ordinary matter inside it grew with it. Small proto-galaxies merged to form larger ones. Larger ones merged to form the ancestors of the galaxies we see today. The Milky Way itself, according to this model, is the product of dozens or even hundreds of smaller systems that collided and merged over billions of years, gradually assembling into the grand spiral structure we inhabit now. This picture is not a guess. It is supported by some of the most rigorous and successful computer simulations ever constructed. Programs like the Millennium Simulation, the Illustris project, and its successor Illustris TNG have modeled the growth of cosmic structure from those initial tiny ripples in the background radiation all the way forward to the present day. They track millions of dark matter particles, billions of years of mergers, and the physics of gas cooling, star formation, and black hole growth across volumes of space large enough to contain thousands of galaxies. The results match the observed universe with remarkable fidelity. The distribution of galaxies on the largest scales, the clustering patterns, the relative numbers of different galaxy types at different distances, the filamentary structure of the cosmic web, the vast network of matter that connects galaxy clusters across hundreds of millions of light years. When scientists talk about the standard model of cosmology, known formally as lambda CDM, they are referring to this entire framework. Lambda represents dark energy, the mysterious force accelerating the expansion of space. CDM stands for cold dark matter, the invisible scaffolding that guides the assembly of structure. Together, lambda CDM describes a universe that began hot and smooth, cooled over time, and built complexity through hierarchical merging over billions of years. It is the most tested, most confirmed, and most widely accepted model in the history of cosmology. And it tells a very specific story about what the early universe should look like. Go back far enough to within the first 500 million years or so after the Big Bang, and you should find a cosmos that is still under construction. The first stars have ignited, but the first galaxies are small, faint, and irregular. They have not had time to merge into large systems. They haven't had time to build organized structures like spiral arms or central bars. They have not had time to enrich their gas with multiple generations of heavy elements. They have not had time to grow supermassive black holes at their centers, at least not large ones. And they certainly have not had time to exhaust their gas supplies and stop forming stars. Everything at that epoch should be young, raw, and still very much in progress. That is the prediction. And for a long time, it held. The Hubble Space Telescope, launched in 1990, was the primary tool for studying distant galaxies for over 3 decades. Hubble could see far back in time, observing galaxies as they appeared billions of years ago. And what it found broadly agreed with the hierarchical picture. Distant galaxies were smaller, more irregular, and less organized than nearby ones. The further back Hubble looked, the more chaotic the universe appeared. The trend was clear. The past was simpler. The present was more complex. Time built structure. Everything pointed in the same direction. Hubble's contribution to this confidence cannot be overstated. Over its lifetime, the telescope conducted some of the deepest observations ever made of the distant universe. the Hubble Deep Field in 1995, the Ultra Deep Field in 2004, the Frontier Fields program in the mid-2010s, each one stared at a tiny patch of sky for days or weeks at a time, collecting every photon that arrived from the farthest reaches of the cosmos. The resulting images contained thousands of galaxies stretching back over 12 billion years of cosmic time, a visual record of how the universe evolved from youth to maturity, and the record confirmed the story. Galaxies at high redshifts, seen as they were in the first few billion years, were smaller and clumpier than their modern counterparts. They showed irregular shapes, signs of ongoing mergers, and evidence of active, vigorous star formation. They were building themselves in real time, assembling mass through the slow accumulation of smaller pieces. Galaxies at lower redshifts, seen as they were in the more recent past, were larger, more organized, and more settled, and spiral arms had developed. Elliptical galaxies had formed through major mergers. The cosmic web of filaments and voids had become more sharply defined. The progression from simple to complex was visible in the data, frame by frame, epoch by epoch, exactly as the models predicted. There were occasional oddities, a galaxy here or there that seemed slightly too massive or too bright for its distance. A quasar, a blindingly luminous point of light powered by a supermassive black hole, found at an uncomfortably early epoch. But these were edge cases. They could be explained by unusual circumstances, statistical flukes, or measurement uncertainties. They did not break the model. They scratched it. And scratches, in science, are expected. No model is perfect. What matters is whether the broad picture holds. And for decades, it did. Hubble did push two remarkable distances. It detected galaxies at redshift 8, 9, and even a candidate or two near redshift 11, corresponding to just 400 million years after the Big Bang. But at those extreme distances, even Hubble was straining. The galaxies were faint. Their light stretched deep into the near-infrared, where Hubble's sensitivity dropped off. The telescope could tell that they were there, could measure their approximate brightness and estimate rough distances, but it could not characterize them in detail. It could not measure their masses precisely. It could not analyze their chemical compositions. It could not resolve their internal structures. The most distant galaxies Hubble found were little more than smudges, a few pixels of light on a detector, hinting at the presence of something, but unable to reveal what that something actually was. This was not a failure of the telescope. It was a limitation of the physics. The most distant galaxies emit most of their light in ultraviolet wavelengths, which get stretched by the expansion of space into the infrared. Hubble's instruments were optimized for visible and near ultraviolet light. It could detect some near-infrared radiation, but it was not designed to operate primarily in that range. To truly see the first galaxies, to study them in the same detail that Hubble had brought to the nearer universe, required an entirely different kind of observatory. The cosmic microwave background confirmed the initial conditions. The galaxy surveys confirmed the large-scale structure. The simulations confirmed the growth timeline. The chemistry of distant stars confirmed the enrichment history. Everything fit. Not perfectly, never perfectly, but well enough that cosmologists had earned the right to feel confident. The story of the early universe was not complete, but its outline was settled. The universe began simple. Gravity built complexity. Time was the essential ingredient. And you needed a lot of it. This is the version of the story that most people carry in their heads, whether they know it or not. The idea that the cosmos started from almost nothing, that the first structures were fragile and crude, that the grand architecture of galaxies and clusters and the cosmic web took billions of years to assemble. It is a comforting story, in a way that most people do not consciously recognize. It implies order. It implies patience. It implies that the universe follows rules we understand, and that those rules operate on timescales we can calculate. It is a story that says, we know where things came from, we know how they got here, and the process was slow enough that we can track it, step by step, from the beginning to now. That comfort is not a small thing. It is the foundation on which an entire field of science rests. It is the reason textbooks can be written, courses can be taught, and grant proposals can be funded with confidence. It is the reason a graduate student can spend 5 years modeling the formation of a single type of galaxy and trust that the framework they're working within is sound. It is the quiet certainty that sits underneath every paper, every simulation, every press release about the early universe. We understand the broad strokes, the details are still being filled in, but the canvas is secure. Except the canvas depends on one assumption that no one questioned, because no one had the tools to test it directly. The assumption is that when we finally looked at the universe as it existed in those first few 100 million years, with enough resolution and enough sensitivity to see what was actually there, the picture would match what the models predicted. Small, faint, chaotic, young-looking structures still in the earlier stages of assembly. That is what should be there. That is what every simulation produces. That is what the math says. And for decades, we could not check. Hubble was extraordinary, but it had limits. Its mirror was 2.4 meters across. It observed primarily invisible and near ultraviolet light, and the most distant, youngest galaxies in the universe do not emit much visible light at all. Their light has been stretched by the expansion of space, shifted from ultraviolet and visible wavelengths deep into the infrared. To see those galaxies, you need an infrared telescope, a big one, a cold one positioned far enough from Earth to escape the thermal glow of our planet's atmosphere. You need the James Webb Space Telescope. Webb launched on December 25th, 2021, from a European Space Agency launch site in French Guiana, aboard an Ariane 5 rocket. It traveled for roughly 30 days to a point in space called the L2 Lagrange point, approximately 1.5 million kilometers from Earth, on the side opposite the Sun. At L2, the telescope orbits the Sun in lockstep with our planet, permanently shielded from the Sun's light and heat by a tennis court-sized sun shield that keeps its instruments at a temperature of roughly negative 233 degrees Celsius. Its primary mirror is 6.5 meters across, nearly 3 times the diameter of Hubble's. It collects more than 6 times as much light, and it observes in the infrared precisely the wavelength range where the most ancient galaxies in the universe are visible. Webb was designed from the first sketches on paper in the late 1980s to answer a specific set of questions about the early cosmos. When did the first galaxies form? How did they grow? What did they look like? How did the first stars enrich the universe with heavy elements? When did the first supermassive black holes appear? The telescope was expected to find answers that refined and deepened the existing story. It was expected to fill in the details of a picture whose broad outlines were already secure. Nobody launched a $10 billion space observatory expecting it to make the early universe look wrong, but that is what happened. In July of 2022, barely 6 months after launch, Webb released its first batch of deep field images. These were exposures of small patches of sky, seemingly empty to the naked eye, observed for hours at a time in multiple infrared wavelengths. The images were dense with galaxies, thousands of them in every frame, tiny red smudges, each one a galaxy seen as it appeared billions of years ago, its light stretched by the expansion of the cosmos across incomprehensible distances. The scientific community expected those red smudges to be small, faint, and messy. Infant galaxies barely forming their first stars, and some of them were exactly that, but others were not. Some were far too bright, some were far too massive. Some appeared to contain billions of stars worth of material, packed into compact, luminous structures that by every model in existence should not have had time to assemble. Within weeks, the first papers began appearing on preprint servers. The tone was cautious at first. Researchers used words like tension and unexpected and intriguing. They double-checked their photometric estimates. They flagged the need for spectroscopic confirmation. They noted that early measurements might be contaminated by active black holes mimicking the signatures of massive star populations. All of that was appropriate. All of it was responsible science. But underneath the caution, something had shifted. The early universe, as seen through Webb's infrared eyes, did not look like the beginning everyone expected. It looked older, more developed, more structurally mature, more chemically enriched, more organized. The comfortable story, the one that said the cosmos built complexity slowly and patiently over billions of years, had just been shown a picture of its own youth, and the face staring back did not match the baby photo. That was the summer of 2022. Webb had been operational for less than a year. The data was preliminary. The measurements needed confirmation. The community held its collective breath and waited for follow-up observations, spectroscopic redshifts, and more refined analyses that would either resolve the tension or deepen it. The follow-up came. The spectroscopy came, the refined analyses came, and the tension deepened. Not by a little, not in one direction. In every direction Webb pointed, at every epoch it examined, the same signal kept appearing. The early universe was more developed than it was supposed to be. Not slightly more. Not within the comfortable margins of model uncertainty, more in ways that forced researchers to use the word challenge when talking about the frameworks they had spent their careers building. What happened next was not a single headline. It was a cascade. Discovery after discovery, paper after paper, each one adding another data point to a pattern that refused to resolve into comfortable agreement with the predictions. Galaxies too massive, black holes too heavy, chemistry too advanced, structure too organized, death too early. The comfortable story was not collapsing. That would be dramatic, and drama is easy to process. Instead, the story was being slowly, steadily, persistently pressured by a telescope that kept looking backward in time and finding a cosmos that did not match the simple version of its own beginning. The cracks were forming, and each new observation made them a little wider. To understand why the early Webb data unsettled the scientific community so quickly, you need to appreciate what researchers expected to find when they finally looked at the universe as it existed within its first billion years. The predictions were specific. Computer simulations running the standard lambda CDM model forward from those initial ripples in the cosmic microwave background, produced a clear forecast. At 500 million years after the Big Bang, the most massive dark matter structures should contain roughly 1 billion solar masses of total matter. The galaxies forming inside those structures should be small, with stellar masses in the range of tens of millions to perhaps a few 100 million times the mass of our Sun. Star formation rates should be modest. Heavy element abundances should be low, because there simply had not been enough time for multiple generations of stars to live, die, and scatter their enriched remains into the surrounding gas. The morphology of these young systems should be irregular, clumpy, and disorganized, because the merging process that eventually builds large structured galaxies was supposed to be in its earliest and messiest phase. That was what the math said. That was what the simulation showed. And when Webb opened its eyes and looked, something different stared back. The first major disturbance came from a team led by Ivo Labai, an astronomer at the Swinburne University of Technology in Australia. In the summer and fall of 2022, Labai and his colleagues analysed data from two of Webb's earliest deep survey programs, SEERS and a portion of what would become the JADES survey. They were looking for galaxies at extreme distances, systems whose light had been travelling for over 13 billion years, visible only as faint red sources in Webb's near-cam infrared images. What they found were 6 objects that did not make sense. Each one appeared to be a massive, compact galaxy existing when the universe was between 500 million and 700 million years old. That alone was notable. But when the team estimated the stellar masses of these objects using spectral energy distribution modeling, a technique that fits the observed brightness across multiple wavelength filters to infer the properties of the underlying star population, the numbers came back absurdly high. These galaxies appeared to contain between 10 billion and 100 billion solar masses of stars. Not total matter. Stars. Already formed, already burning, already assembled into systems comparable in stellar mass to the Milky Way itself. The Milky Way took over 13 billion years to reach its current mass. These objects appeared to have accomplished something similar in roughly 500 million years. The universe, at the moment these galaxies were being observed, was roughly 3% of its current age. The team gave these objects an informal name that captured the magnitude of the problem. They called them universe breakers. The reason the name stuck is because the numbers, if correct, genuinely threatened to break the standard model, not scratch it, not pressure it, break it. Here is why. In lambda CDM cosmology, there is a hard limit on how much ordinary matter can collapse into any given dark matter structure by a given time. The total amount of ordinary matter in the universe is fixed. It makes up roughly 15% of all matter, with the rest being dark matter. At any moment in cosmic history, the amount of baryonic material available to form stars within a particular dark matter halo is constrained by the size of that halo and the overall cosmic density. Michael Boylan Colchin, a theoretical astrophysicist at the University of Texas at Austin, ran the calculation. He asked a simple question. If you take the largest dark matter structures that the standard model predicts should exist at that epoch, and you convert every single baryon inside them into stars with 100% efficiency, wasting nothing, losing nothing to heating, radiation pressure or outflows, could you produce galaxies as massive as the ones Labé's team reported? The answer, published in a paper that circulated widely through the community, was barely. Some of the reported masses were right at the theoretical ceiling, and a few appeared to exceed it. That meant either the measurements were wrong, or the standard model was underestimating how much matter was available, or star formation in the early universe operated with an efficiency so extreme that it defied every known physical mechanism for converting gas into stars. The community responded with appropriate caution. Photometric estimates of stellar mass are notoriously uncertain, especially at extreme distances. The light from an actively feeding supermassive black hole can mimic the spectral signature of a massive star population, inflating the inferred stellar mass. Dust can alter the observed colors in ways that confuse the modeling. And the filters Webb uses, while far superior to anything available before, were still being calibrated in those early months of operation. It was entirely possible that some or all of the universe breakers would shrink in mass once spectroscopic confirmation replaced the preliminary photometric estimates. And some of them did shrink. Over the following 2 years, as Webb's spectrographic instruments were brought to bear on these and similar objects, several of the most extreme mass estimates were revised downward. Some turned out to be powered partly by active black holes rather than pure star formation. Some turned out to be at slightly different distances than initially estimated. The most headline-grabbing numbers, the ones that seemed to flatly violate lambda CDM, softened, but they didn't disappear. Even after revision, the population of galaxies Webb was finding in the first billion years remained significantly more massive, more luminous, and more numerous than the standard model had predicted. The tension was not eliminated by better data, it was refined. The question shifted from, are these measurements real, to why are there so many bright, massive galaxies so early? That second question is harder to dismiss, and it has not gone away. By 2024 and into 2025, multiple large survey programs have confirmed the pattern with a statistical confidence. The ultraviolet luminosity functions, which describe how many galaxies of a given brightness exist at each epoch, showed surprisingly little decline at the bright end beyond redshift 10, corresponding to roughly 470 million years after the Big Bang. There were simply more bright galaxies at these extreme distances than any pre-Webb theoretical model had predicted. Not one or two anomalous objects that could be explained away as statistical flukes. Dozens, then hundreds, a population, and the record for the most distant confirmed galaxy kept being pushed further back. In January of 2026, a study led by Rohan Naidu at the Massachusetts Institute of Technology's Kavli Institute for Astrophysics and Space Research announced the spectroscopic confirmation of MOMSI 14, the most distant galaxy ever observed. Its light had been traveling for over 13.5 billion years. It was visible as it existed just 280 million years after the Big Bang. That number requires a moment to absorb. 280 million years is an enormous span of time by human standards, but in cosmological terms, it is a sliver. The universe at that moment was roughly 2% of its current age, and there, in that sliver, was a galaxy. Not a hypothetical smudge at the edge of detectability. A confirmed object, spectroscopically verified, bright enough to be characterized. Naidu described the finding in terms that captured the wider mood. With Webb, he said, we are able to see farther than humans ever have before, and it looks nothing like what we predicted. That last clause is the one that carried the weight. It looks nothing like what we predicted. This was not a minor recalibration. It was a direct admission that the observations were diverging from the models in a fundamental way. The implications rippled outward into related areas of the standard model. If galaxies were assembling faster than expected, something about the physics governing their formation needed adjustment. Either star formation efficiency in the early universe was dramatically higher than in the modern cosmos, or the dark matter structures hosting these galaxies were more massive than models predicted, or the initial conditions from which structure grew were different from what the cosmic microwave background measurements implied. Each of these possibilities carried its own set of consequences, and none of them was comfortable. But the massive early galaxies were only one front in what was becoming a multi-directional assault on the comfortable timeline. While some teams were grappling with the stellar mass problem, others were confronting a different version of the same fundamental issue: supermassive black holes that were far too heavy for their age. In the local universe, the relationship between a supermassive black hole and the galaxy hosting it follows a remarkably consistent pattern. The black hole typically contains between roughly 0.1 and 0.5% of the galaxy's total stellar mass. This ratio holds across a wide range of galaxy types and sizes, and it implies a deep connection between how black holes grow and how their host galaxies evolve. They grow together. They regulate each other. The black hole's energetic outbursts heat surrounding gas and slow star formation. The galaxy's gas supply feeds the black hole. Over billions of years, this feedback loop produces the tight mass relationship observed in the modern cosmos. Webb shattered that relationship in the early universe. When astronomers used the telescope's near-spec instrument to measure the masses of supermassive black holes in galaxies within the first 1 to 2 billion years after the Big Bang, they found something deeply wrong. The black holes were too heavy, not by a small margin. The ratio of black hole mass to host galaxy stellar mass was frequently 10 to 100 times higher than the local relationship. In some extreme cases, the black hole appeared to contain 10 to 30% of its host galaxy's total stellar mass, a ratio 100 to 1,000 times above what the local universe would predict. This is not a subtle discrepancy. In the modern cosmos, if the Milky Way's central black hole, Sagittarius AI star, followed these ratios, it would need to be hundreds of times more massive than it actually is. The early universe black holes were not just bigger than expected relative to their galaxies. They were dominating their hosts in a way that has no analog in the nearby universe. One of the most striking examples arrived not from Webb alone, but from a collaboration between Webb and the Chandra X-ray Observatory. In 2023, a team led by Akosh Bogdan at the Center for Astrophysics at Harvard and the Smithsonian identified an object designated UHZ1, a galaxy observed at a redshift corresponding to just 470 million years after the Big Bang. The cosmos at that moment had existed for less than 470 million years. And inside that infant galaxy sat a supermassive black hole, so massive relative to its host that the standard coevolution relationship could not begin to explain it. The black hole appeared to have a mass comparable to the entire stellar mass of the galaxy surrounding it. Not 0.1%, not 1%, comparable. The black hole was not a passenger inside its galaxy. It was the dominant gravitational presence. The galaxy was almost an afterthought, a thin halo of stars clinging to the edges of a gravitational colossus that had no business being that large that early. UHZ-1 became one of the strongest pieces of evidence for non-standard black hole formation in the early universe. Its mass and timing were consistent with what theorists call a direct collapse black hole, an object born not from the death of a star but from the catastrophic gravitational implosion of a massive primordial gas cloud. The fact that such an object was needed to explain UHZ-1 tells you how far outside the standard framework this discovery fell. The conventional pathway, a stellar remnant growing through steady accretion, was not merely insufficient. It was irrelevant. The numbers did not even come close. The problem intensified when researchers considered the broader population. The standard growth mechanism for black holes is accretion, the process of pulling in surrounding gas and converting its gravitational energy into radiation. But accretion has a speed limit. It is called the Eddington limit, named after the British astrophysicist Arthur Eddington, and it describes the maximum rate at which a black hole can consume matter before the radiation it produces becomes so intense that it blows away the incoming fuel. A black hole feeding at the Eddington limit doubles its mass roughly every 45 million years. Start with a seed black hole of a few hundred solar masses, the kind left behind by the death of a massive first-generation star, and feed it continuously at the Eddington limit from the moment the first stars formed. By the time the universe is 700 million years old, that black hole reaches roughly 1 million solar masses. That is large, but it is nowhere near the hundreds of millions of solar masses Webb was finding in some early galaxies. The arithmetic simply does not work. There is not enough time. Several theoretical pathways have been proposed to address this problem. One involves direct collapse black holes, which, as the UHZ-1 case illustrates, could start at 10,000 to 100,000 solar masses, giving them a significant head start. Another involves episodes of super Eddington accretion, periods where a black hole manages to consume matter faster than the nominal limit, perhaps because the geometry of the infalling gas allows radiation to escape along certain directions while matter continues flowing in from others. A third involves primordial black holes, hypothetical objects formed from extreme density fluctuations in the first fraction of a second after the Big Bang, which would have been sitting in the darkness for hundreds of millions of years before the first stars even formed. Each of these ideas is physically plausible. None of them is confirmed, and the fact that the field needs to invoke mechanisms that have never been directly observed in order to explain the population Webb is finding tells you something about the severity of the tension. This standard pathway, stellar death, followed by steady Eddington limited accretion, cannot produce what the telescope is seeing. Something else happened in the early universe, something faster, more violent, or more exotic than the comfortable model accounted for. A study published in 2026, using simulations to model the formation of these overmassive black holes, found that direct collapse black holes forming in primordial dark matter halos could reproduce the observed ratios, but only if those seeds also suppressed early star formation in their host galaxies through powerful feedback. The black holes in this picture grew first. The galaxies caught up later. That is the opposite of the co-evolution story that governs the modern universe, and it implies that the earliest epoch of cosmic history operated under fundamentally different rules of engagement between black holes and their galactic homes. The conductor appeared before the orchestra had been hired. Meanwhile, a separate line of evidence published the same year complicated the picture further. A large spectroscopic survey stacking the spectra of many faint early galaxies found that when you look at the full population rather than just the brightest outliers, many early black holes fall within a more normal mass range. The apparent overabundance of overmassive black holes may be partly a selection effect. The most massive, most luminous ones are the easiest to detect, which biases the observed sample toward extremes. This does not eliminate the tension. It means the full population is more complex than the headline objects suggest, which is itself a form of tension, because the models need to explain not just the monsters, but the entire distribution. Woven through the black hole discoveries was a population of objects that refused to be classified cleanly and that amplified every tension simultaneously. The objects known as little red dots. These are compact, luminous sources scattered throughout Webb's deep survey images, appearing as tiny crimson points of light in the early universe. Hundreds of them have been catalogued since Webb began operating. Their nature remains one of the most actively debated questions in extragalactic astronomy. The little red dots share a distinctive observational signature. They are extremely compact, appearing point-like, or nearly so even in Webb's sharpest images. They show a characteristic color profile, relatively blue in the ultraviolet and short wavelength infrared, but steeply red at longer wavelengths. And they are far more numerous than any pre-Webb model predicted for any population of objects at those redshifts. The debate centers on what powers them. If the dominant energy source is an actively feeding supermassive black hole, then the little red dots represent a previously unknown and surprisingly abundant population of active galactic nuclei at high redshift. That interpretation would intensify the overmassive black hole problem dramatically, because it would mean that not just a handful of extreme outliers, but a large, common population of black holes was actively accreting in the early universe. If the dominant energy source is star formation, then these objects represent the most extreme stellar densities ever observed, packing enormous rates of star production into volumes so small that they appear unresolved even to Webb's instruments. Observations have not yet converged on a definitive answer, and the truth may be a mixture. Some little red dots show broad emission lines in their spectra, a hallmark of gas orbiting at high velocity near a supermassive black hole. Others lack those signatures. Stacking analyses in X-ray and radio wavelengths, which should detect emission from actively feeding black holes, have yielded ambiguous results, with some studies finding faint signals and others finding none. A mini-review published in early 2026 described the identity of the little red dots as highly debated, noting that if they are primarily black hole driven, they help explain the rapid growth of the most massive black holes found by Webb in the first billion years. The little red dots are important not because they resolve the tension, but because they embody it. They sit at the intersection of the galaxy mass problem and the black hole mass problem, and they refuse to be absorbed into either framework cleanly. They are something new. And their sheer abundance in Webb's deep fields, hundreds of objects where pre-Webb models predicted few or none, is itself a statement about how poorly the standard models captured the true complexity of the early cosmos. And then there were the dead galaxies. If finding massive galaxies too early was disturbing, and finding overmassive black holes too early was worse, then finding galaxies that had already stopped forming stars at an epoch when star formation should have been at its most vigorous was something else entirely. It was like walking into a newborn ward and finding a teenager. In 2025, an international team led by astronomers at the University of Geneva announced the discovery of the most distant massive quenched galaxy ever confirmed. The object, designated Ruby's UDSQGZ7, had formed roughly 15 billion solar masses worth of stars, and then stopped. Completely. Its star formation had shut down by the time the universe was only 700 million years old. This galaxy was not slowly winding down. It was not transitioning from an active phase to a quieter one. It had already finished. The stellar population was aging. The gas that fuels star formation was either gone or rendered unable to collapse. The galaxy had lived fast and died young, but at a speed that defies every mechanism cosmologists use to explain quenching. In the modern universe, massive galaxies typically quench over billions of years. The process involves a combination of internal and external mechanisms. Energetic outflows from a central supermassive black hole can heat surrounding gas and prevent it from cooling enough to form stars. Galaxy mergers can shock heat gas and destabilize star-forming regions. Environmental effects in dense galaxy clusters can strip gas away from member galaxies. Each of these processes takes time, lots of time. The idea that a galaxy could assemble 15 billion solar masses of stars and then quench entirely within the first 700 million years of the universe demands an explanation that no current model provides cleanly. The Ruby's galaxy was not alone. Webb had been finding quenched galaxies at progressively earlier and earlier epochs. Several have been confirmed at redshifts corresponding to 1.2 billion years after the Big Bang. Others were identified, though not yet spectroscopically confirmed, at even earlier times. The population of early dead galaxies was growing, and each new detection pushed the problem further. If quenching can happen this fast, the mechanisms driving it must be extraordinarily efficient, operating on timescales of a few 100 million years or less. That either means the black hole feedback process is far more violent in the early universe than models assume, or there is some other shutdown mechanism at work that nobody has yet identified. A study published in 2025 in collaboration between the University of Geneva and several partner institutions framed the situation directly. Their finding, they wrote, deepen the tension between theoretical models of cosmic evolution and actual observations. That language, from a peer-reviewed paper in a major journal, captures the mood of the community. This is not fringe speculation. This is the professional assessment of the scientists doing the work. While the quenching discoveries were unfolding, another finding arrived that added yet another layer to the accumulating pattern. In 2025, a team at Texas A&M University announced the discovery of a remarkable system. An ongoing merger of at least 5 galaxies observed just 800 million years after the Big Bang. The system was identified through Webb's infrared imaging and confirmed through detailed spectroscopy. 5 galaxies gravitationally interacting, exchanging material, and reshaping their environment at a redshift of 6.7. The merger alone was notable. Galaxy interactions at that epoch were expected to be relatively rare because the structures hosting galaxies were still small and widely separated. Finding a tightly packed group of 5 interacting systems suggested that the cosmic web of dark matter filaments, the large-scale infrastructure that channels galaxies toward each other, was already well developed less than 1 billion years after the Big Bang. That was an uncomfortable finding on its own terms. But the deeper surprise was chemical. Webb's spectroscopy revealed that the collision was redistributing heavy elements beyond the boundaries of the individual galaxies. Carbon, oxygen, and other products of stellar nucleosynthesis had been ejected into the intergalactic space between the merging systems, enriching gas that lay outside any single galaxy. This matters because it demonstrates that the chemical enrichment of the early universe was not confined to the interiors of individual galaxies. It was spreading through the broader cosmic environment at a rate and on a scale that models had not accounted for. The merger was acting as an engine of chemical dispersal, seeding the surrounding medium with heavy elements far earlier and far more efficiently than the standard picture assumed. Now, step back and look at all of these problems together. Galaxies too massive too early. The most distant confirmed galaxy at just 280 million years. Black holes too heavy too early, with objects like UHZ-1 defying every conventional growth pathway. Little red dots, hundreds of unclassified compact sources intensifying both the galaxy and black hole tension simultaneously. Galaxies already dead too early. Multi-galaxy mergers redistributing heavy elements at 800 million years. Each of these observations, taken alone, could potentially be explained by adjusting one parameter or invoking one new mechanism. Star formation efficiency might have been higher, black hole seeds might have been heavier, quenching might have been more efficient, chemical dispersal might have been faster. Fine. Each fix addresses one issue, but the problems are not independent. They are connected. A galaxy that forms an enormous stellar mass very quickly is the same kind of galaxy that might host an overmassive black hole. An overmassive black hole feeding aggressively might produce the kind of violent feedback that quenches star formation on a short timescale. A quenched galaxy at an impossibly early time implies both rapid mass assembly and rapid shutdown, which requires both extreme star formation and extreme black hole activity operating in sequence within a few 100 million years. A multi-galaxy merger at 800 million years implies that the large-scale environment was already structured enough to bring multiple systems into close proximity and violent interaction. Each individual tension is uncomfortable. Together, they outline something more serious. They suggest that the entire pace of cosmic evolution in the first billion years was faster than the standard model anticipated. Not one process was accelerated. Everything was accelerated. Assembly, enrichment, growth, feedback, quenching, environmental development. The early universe was running ahead of schedule across every axis the telescope could measure. This is where the nature of the problem begins to change. Individual anomalies invite targeted explanations. A pattern invites a deeper question. And by the time Webb had been operating for 2 full years, the anomalies had stopped feeling like anomalies. They were converging into a picture, like pieces of forensic evidence at a crime scene that do not individually prove anything, but collectively point in a single direction. The earliest cosmos was further along than anyone had accounted for. Not in one way. In every way Webb could measure. The community recognized this convergence. Papers began appearing that analyzed not just individual objects, but the statistical properties of early galaxy populations as a whole. The ultraviolet luminosity functions, the stellar mass functions, the number density of quenched galaxies as a function of redshift, the black hole mass distributions. Each of these analyses told the same story. There were more of everything. More massive galaxies, more luminous galaxies, more evolved galaxies, more dead galaxies at every early epoch, than the pre-Webb models had predicted. In November of 2025, a team at Maynooth University and the Georgia Institute of Technology published an analysis titled Beyond No Tension, a deliberate response to an earlier paper that had argued the Webb observations could be reconciled with simulations. The new analysis pushed the comparison to higher redshifts, beyond redshift 10, and found that the tension was not resolved. It was getting worse. The simulations were being pushed to their limits, and the most extreme observed galaxies at the highest redshifts still sat above the predictions. The title itself tells you something about how the conversation had shifted. The debate was no longer about whether there was tension between Webb's observations and the standard model. The debate was about how much tension and whether it could be accommodated within existing physics or required something new. That was the state of the field as Webb entered its third and fourth years of operation. The first cracks had widened. The initial caution of "let's wait for spectroscopic confirmation" had been replaced by confirmed spectroscopic measurements that preserved or deepened the discrepancies. The initial hope that better data would make the problem smaller had given way to the recognition that better data was making the problem sharper. And then, the discoveries stopped being about how much stuff existed too early. They started being about what kind of structures existed too early. Not just mass, not just brightness, not just chemistry, but form, organization, architecture. The early universe was not simply overstuffed with matter. It was overstuffed with maturity. The next wave of Webb findings would make the first cracks look like warm-ups, because they would show that the cosmos had not just assembled mass ahead of schedule. It had built finished structures in an era where only scaffolding should exist. Finding too much mass in the early universe was one kind of problem. Finding too much structure was another kind entirely. And the difference between them is the difference between a house that weighs more than the blueprint specified, and a house that was never supposed to be built at all, standing fully finished on a lot where only a foundation pit should exist. Mass can accumulate quickly under the right conditions. If star formation efficiency was higher, if gas cooling was more rapid, if the initial density fluctuations were slightly more extreme than models assumed, you can push the numbers upward without abandoning the basic framework. You can stretch the model. You can dial the knobs. You can argue that the universe was working harder than expected, within the same set of physical rules. Structure is different. A galaxy with spiral arms, a central bar, an organized rotating disk, a distinct bulge. These are not features that appear because more gas collapse faster. They are features that require dynamical settling. They require the gas to lose its chaotic energy, fall into a plane, begin rotating in an orderly fashion, develop density waves that propagate through the disk, and sustain those waves long enough for coherent spiral patterns to emerge. This process, in every simulation ever constructed, takes time. Billions of years of time. You cannot rush it by turning up the star formation rate. The physics of angular momentum, gravitational torques, and disk instability set their own clock. And that clock is supposed to run slowly. Webb found the clock running fast. In December of 2025, two Indian astronomers, Rashi Jain and Yogeshwadadikar, working at the National Center for Radio Astrophysics of the Tata Institute of Fundamental Research in Pune, announced the discovery of a galaxy they named Alaknanda, after a Himalayan river that shares its headwaters with the Mandakini, the Hindi name for the Milky Way. The poetic connection was intentional, because what they had found was a galaxy that looks strikingly like our own, in an era when nothing remotely like it should have existed. Alaknanda is a grand design spiral galaxy. That term has a precise meaning. It describes a galaxy with two clear, symmetric spiral arms extending outward from a bright central region, sweeping gracefully through a flattened disk of stars and gas. Grand design spirals are among the most visually striking objects in the modern universe. Our own Milky Way is one. They're considered a sign of dynamical maturity, a galaxy that has had time to settle into an organized configuration, develop persistent density wave patterns, and maintain those patterns across many orbital periods. Alaknanda existed when the universe was approximately 1.5 billion years old, roughly a tenth of its current age. The galaxy is massive, containing roughly 16 billion solar masses of stars, and it was forming new stars at approximately 20 times the current rate of the Milky Way. Its disk stretches roughly 10 kiloparsecs across, or about 32,500 light-years, making it a substantial system by any measure. Jane and Wadadakar identified it using data from the Uncover survey, one of Webb's deep imaging programs targeting the field around the galaxy cluster Abell 2744, also known as Pandora's cluster. The enormous gravity of the foreground cluster acted as a natural magnifying glass, bending and amplifying the light from Alaknanda and allowing Webb to resolve its spiral structure in remarkable detail. The discovery was published in the European journal Astronomy and Astrophysics. Jan described the finding in direct terms. "The galaxy," she said, "has the structural maturity we associate with galaxies that are billions of years older. Finding such a well-organized spiral disk at this epoch tells us that the physical processes driving galaxy formation, gas accretion, disk settling, and possibly the development of spiral density waves can operate far more efficiently than current models predict." She said it was forcing the team to rethink their theoretical framework. That phrase, "rethink the theoretical framework," had become a recurring motif in Webb-era astronomy by this point. But Alaknanda added a new dimension to the rethinking. This was not about mass. It was not about luminosity. It was about form. The galaxy had not just assembled a lot of stars quickly. It had organized them into a coherent, symmetric, dynamically mature configuration that every simulation said should require several billion additional years of evolution to achieve. Alaknanda was not an isolated case. It was the most dramatic example of a growing class of structurally mature early galaxies that Webb was pulling out of the deep past, each one a challenge to the assumption that the young universe should look young. In February of 2026, a team led by Daniel Ivanov at the University of Pittsburgh reported the identification of Cosmos 74706, a strong candidate for one of the earliest known barred spiral galaxies. Stellar bars are elongated structures of stars stretching across the center of a galaxy, rotating as a single, rigid unit. As they spin, they act as gravitational funnels, channeling gas inward toward the galactic nucleus, triggering bursts of star formation, feeding central black holes, and building up dense cores. Bars are common in the modern universe. The Milky Way has one. But forming a stellar bar requires a disk that has already settled into organized rotation, and the bar itself must grow through gravitational instabilities that operate over hundreds of millions to billions of years. Cosmos 74706 was observed at a time when the universe was approximately 2 billion years old. That is uncomfortably early for a stellar bar to exist. and the discovery added to the mounting evidence that disk galaxy structures were assembling faster than theorists had predicted. Then, in May of 2026, the problem escalated further. A team using Webb and the Atacama Large Millimeter Array announced the discovery of a massive stellar bar in GN20, a galaxy observed just 1.5 billion years after the Big Bang. This was not a tentative detection or a marginal candidate. The bar was approximately 7 kiloparsecs long, a substantial structure embedded in an extreme gas-rich disk. The finding defied expectations in 3 distinct ways. First, bars in high-density systems were thought to be prone to collapse under their own gravitational weight. Second, growing a bar that large should take billions of years. Third, high gas fractions in early galaxies were thought to suppress or delay bar formation entirely, because the turbulent, gas-dominated disks of the young universe should resist the kind of gravitational instabilities that bars require. The team found that all 3 obstacles could be overcome by a single ingredient directly supported by the observations: the presence of highly turbulent gas across the inner disk. The turbulence appeared to stabilize the bar and allow it to grow quickly, providing a pathway for early galaxies to develop these complex structures far faster than previously expected. The bar, once formed, acted as a funnel, driving gas inward and potentially feeding both the central black hole and a burst of concentrated star formation that could eventually exhaust the gas supply and quench the galaxy. This discovery linked structural maturity directly to the quenching problem described earlier. The bar was not just a cosmetic feature, it was a mechanism, and it was operating billions of years ahead of schedule. While some teams were documenting the impossible maturity of individual galaxies, others were finding that the large-scale environment of the early universe was similarly more developed than it should have been. In January of 2026, a collaboration using both Webb and the Chandra X-ray Observatory announced the detection of a protocluster designated JADES ID1. A protocluster is the embryonic precursor to a galaxy cluster, one of the largest gravitationally bound structures in the universe. Modern galaxy clusters contain hundreds or thousands of galaxies embedded in a vast halo of dark matter and hot gas, with total masses reaching thousands of trillions of solar masses. They are the cities of the cosmos, and like cities, they take a very long time to build. JADES ID1 was observed assembling just 1 billion years after the Big Bang. Its mass was estimated at roughly 20 trillion solar masses. The previous record holder for a protocluster with detectable X-ray emission, a signature of hot gas settling into the cluster's gravitational potential, was observed much later, at roughly 3 billion years after the Big Bang. JADES ID1 pushed the timeline back by 1 to 2 billion years, landing in an epoch where most models said a structure of this size simply should not yet exist. The researchers framed the discovery carefully. They acknowledged that finding a protocluster this early placed it in tension with the predictions of most cosmological models, which did not produce enough time or a high enough density of galaxies for a structure of this scale to form within the first billion years. The previous detections of surprisingly large early galaxies and black holes had already made the community uneasy. Finding that the environment those galaxies inhabited, the large-scale scaffold holding them together, was also more developed than expected, added a new layer to the problem. It was no longer just individual objects that were too mature. The cosmic infrastructure supporting those objects was ahead of schedule too. A separate line of evidence, quieter in the headlines but equally significant in the journals, was accumulating around chemical enrichment. The Alpine Crystal Survey, an international collaboration of more than 50 scientists across more than 15 institutions, presented results in January of 2026 at the American Astronomical Society meeting. Their findings, published in the Astrophysical Journal supplement, described a systematic survey of galaxies in the early universe, conducted with Webb. The key result was that galaxies observed within the first 1 to 2 billion years were maturing faster in several ways than researchers had believed. Specifically, they were more chemically enriched than expected. They had produced more heavy elements, particularly carbon and oxygen, than was thought possible at such an early cosmic age. This matters because heavy elements do not appear from nothing. They are forged inside stars through nuclear fusion. Carbon is produced in the cores of massive stars. Oxygen is produced in even more massive stars and in supernova explosions. Distributing these elements into the gas surrounding a galaxy requires those stars to live their lives, die in explosions, and scatter their enriched material into the interstellar medium, where it mixes with primordial hydrogen and helium before being incorporated into the next generation of stars. This recycling process is supposed to take hundreds of millions of years per cycle, and building up the levels of enrichment Webb was observing should have required multiple cycles, multiple generations of stars living and dying and feeding their products back into the system. The Alpine crystal results indicated that this chemical recycling was happening much faster than models predicted. The early universe was not merely assembling mass quickly. It was processing that mass through stellar life cycles at an accelerated rate, producing and distributing heavy elements with an efficiency that the standard enrichment models could not comfortably reproduce. This connected directly to the structural maturity problem, because a galaxy that is chemically enriched is a galaxy that has already lived through a significant portion of its evolutionary history. Chemistry is a clock, and the chemical clocks Webb was reading kept showing times that were too advanced for the epoch. In a study from the University of Cambridge published in the monthly notices of the Royal Astronomical Society, a team led by Sandro Tarkel analyzed more than 250 young galaxies observed by Webb at epochs between 800 million and 1.5 billion years after the Big Bang. Their focus was not on mass or chemistry, but on dynamics, specifically on how the gas inside these galaxies was moving. They found that most of the galaxies were turbulent, clumpy systems that had not yet settled into smooth, rotating disks. This was broadly consistent with expectations. Most early galaxies should be messy. But the study also found that the degree of turbulence and the rate at which galaxies were settling into organized rotation varied more widely than models predicted. Some galaxies at these early epochs were already remarkably well ordered, while others remained chaotic. The diversity itself was the finding. The early universe was not uniformly primitive. It was a mixed population, with some systems far more dynamically mature than their neighbors at the same epoch. That heterogeneity is hard to explain if all galaxies at a given time are evolving at roughly the same pace, through the same set of physical processes. Something was allowing certain galaxies to fast-track their way to maturity while others lagged behind. And then, in May of 2026, Webb delivered perhaps the most conceptually jarring finding in this entire sequence. A team of astronomers reported the discovery of a massive galaxy, designated XMMVID 12075, observed when the universe was approximately 1.8 billion years old. The galaxy was massive. It had already stopped forming stars. It was quenched, dead, finished. But that was not what made it strange. What made it strange was that it showed no measurable rotation. The measurement was not ambiguous. The team used Webb's integral field spectroscopy capability, an observational technique that collects a full spectrum at every point across the face of a galaxy simultaneously. This produces a two-dimensional map of how gas and stars are moving at every location within the system. In a rotating galaxy, this map shows a characteristic pattern. One side of the galaxy is moving toward the observer. The other side is moving away, and the velocity shifts smoothly from one edge to the other. The stronger the rotation, the steeper the gradient. In nearby galaxies, this technique has been used for decades to measure rotation curves with exquisite precision. Webb's near-spec instrument, configured in its integral field unit mode, brought that same diagnostic power to a galaxy more than 12 billion light-years away. What the velocity map of XMMVID 12075 showed was essentially nothing. No gradient, no organized flow. The stars within the galaxy were moving, but not in a coherent rotational pattern. Instead, their motions were random, orbiting the center of mass on individually chaotic trajectories rather than participating in an organized disk. Astronomers describe this as a dispersion-dominated system, one where the internal velocity dispersion, the random scatter in stellar motions, far exceeds any ordered rotational component. The galaxy was being held together by gravity, but the stars inside it moved more like bees in a swarm than cars on a highway. In the standard picture, massive galaxies acquire angular momentum as they form. Gas falls into dark matter halos along filaments, carrying angular momentum with it. The gas settles into a disk. The disk rotates. Stars form within the rotating disk. Over time, mergers can disrupt the disk and transform a spinning spiral galaxy into an elliptical galaxy with less organized motion. But even elliptical galaxies in the modern universe retain some residual rotation from their formation history. A massive galaxy with essentially zero rotation implies a formation pathway so violent, so dominated by chaotic mergers or some other scrambling mechanism, that all organized angular momentum was erased. The research team did not observe XMMVID 12075 in isolation. They targeted 3 massive quenched galaxies at similar redshifts, all roughly the same cosmic age, all dead, all drawn from the same survey of the magazine program. The comparison was deliberate and the result was striking. One of the 3 galaxies showed clear, organized rotation, a velocity gradient consistent with a system that had retained significant angular momentum from its formation. The other 2 showed progressively less rotation, with XMMVID 12075 at the extreme end, showing none at all. 3 galaxies at the same epoch, all massive, all quenched, but with dramatically different internal dynamics. One was spinning, one was barely spinning, one had stopped entirely. This diversity within a single redshift bin is what made the findings so conceptually important. The early universe was not just producing one flavor of premature maturity. It was generating a full spectrum of evolutionary endpoints simultaneously. Some early galaxies were organized spirals with bars. Some were turbulent clumps still assembling. Some were dead disks that retained their rotation. And at least one was a dead, non-rotating giant whose internal structure resembled the most evolved elliptical galaxies in the modern universe, objects that in the nearby cosmos are the final products of billions of years of merging and dynamical relaxation. Finding such a galaxy in the modern universe would be notable, but not shocking. Massive elliptical galaxies nearby sometimes show very low rotation, but finding one less than 2 billion years after the Big Bang, already quenched and already dynamically settled into a non-rotating configuration, demands an evolutionary history that is extraordinarily compressed. This galaxy had to form a massive stellar population, quench its star formation, and undergo whatever process eliminated its rotation, all within roughly 1.5 billion years or less. The most likely pathway to zero rotation involves multiple major mergers, collisions between galaxies of roughly comparable mass arriving from random directions. When two similarly sized galaxies collide head-on, their orbital angular momenta can partially cancel. When a third arrives from a different angle, more cancellation occurs. Enough mergers from sufficiently random directions can effectively erase any net rotation, leaving behind a pressure-supported swarm of stars with no organized spin. But this pathway has a hidden implication. For XMMVID-1 2075 to have undergone multiple major mergers by the time the universe was 1.8 billion years old, each of the merging predecessors had to have already formed, assembled significant mass, and been in close enough proximity to collide. Those predecessor galaxies themselves needed time to form, and their predecessors needed time before that. The non-rotating dead galaxy is not just evidence of one object's rapid evolution. It is evidence of an entire invisible chain of earlier galaxies that had to form, grow, and merge in sequence within the available time. The object we observe is the final product, but the process that built it reaches back much further, implying a population of massive systems at even earlier epochs that have since been consumed and erased by the mergers that created their descendant. The researchers noted that this discovery could reshape ideas about mergers, gas inflow, quenching, and the role of black holes in shutting galaxies down. It was forcing the models to explain not just what existed in the early universe, but the full diversity of evolutionary states, from turbulent clumpy systems to organized spirals to non-rotating dead giants, all coexisting at the same epoch. By early 2026, the accumulated weight of these discoveries had shifted the conversation in a way that no single finding could have achieved on its own. It was no longer possible to treat the early universe tensions as a collection of isolated curiosities. The massive galaxies, the overmassive black holes, the early quench systems, the spiral arms, the stellar bars, the protoclusters, the chemical enrichment, the dynamical diversity, the non-rotating dead giants, the little red dots, each one, taken individually, admitted potential explanations within or near the boundaries of the existing framework. Adjust star formation efficiency here. Invoke a new black hole seeding mechanism there. Allow for enhanced turbulence-driven bar formation. Modify the feedback prescriptions. But the explanations did not add up to a single coherent revision. They were patches applied to different parts of the same model, and each patch addressed a different symptom without treating the underlying condition. The underlying condition was this: across every observable property that Webb could measure, the earliest visible universe was systematically more developed than the pre-Webb consensus expected. Mass, structure, chemistry, dynamics, black hole growth, large-scale environment, quenching, morphological diversity. Every axis showed the same directional offset. Too much, too soon. A paper from late 2025, synthesizing results across multiple survey programs, described the situation as follows. The presence of massive, bright, structurally mature galaxies at high redshifts, combined with over-massive black holes and early quenching, required at least moderately enhanced star formation efficiency at high redshift or tuning of the cosmological model. A coherent explanation for the subtle timing of the emergence of these mature systems and the more apparent galaxy abundance discrepancies, the authors wrote, remains to be identified. That final clause is the one that matters most. Remains to be identified. The community knows what the observations are showing. The community does not yet agree on why. And the longer the why remains open, the more pressure accumulates on the comfortable version of the early universe that everyone carried in their heads before Webb launched. The pattern is not ambiguous. Each new observing cycle, each new data release, each new spectroscopic confirmation adds another piece to a picture that keeps pointing in the same direction. The early universe was not the primitive, under construction, slowly assembling place that decades of modeling led everyone to expect. It was richer, faster, more structured, and more mature than the story allowed. And the word that keeps appearing in the titles of the papers, in the abstracts, in the discussions at conferences, is the same word that appears in the title of this story. Tension. Not crisis, not collapse, not revolution. Tension. The observations and the models are pulling in different directions, and the gap between them has not closed with more data. It has widened. Each new Webb finding tightens the string a little further. And the question that now confronts the entire field is not whether the tension is real. Everyone agrees it is real. The question is what it means. Whether the early universe is telling us that the standard model needs adjustment within its existing framework, or whether it is telling us something deeper. Something about the initial conditions of the cosmos, or the nature of dark matter, or the physics of the first moments after the Big Bang that the comfortable story never accounted for. That question, and the unsettling possibility it opens, is where the final piece of this story begins. The most natural response to everything described so far is to ask whether the standard model of cosmology is broken. That question appears in headlines. It circulates on social media. It carries a dramatic charge that makes it satisfying to ask, and even more satisfying to answer, with a confident yes or no. But the honest answer, the one that the scientists closest to the data would give you if you sat them down in a quiet room, is neither. The standard model is not broken. It is stressed. And the difference between those two words matters enormously, because broken implies replacement, and stressed implies something harder to process. Stress means the framework still works in most of the places it has always worked. The cosmic microwave background still matches the predictions with extraordinary precision. The large-scale distribution of galaxies still follows the patterns the simulations produce. The expansion history of the universe, measured through supernovae and baryon acoustic oscillations, still agrees with lambda CDM across most of cosmic time. The standard model did not suddenly become wrong about everything. It became wrong, or at least uncomfortably incomplete, about a specific era, the first billion years. That specificity is what makes the problem so difficult to resolve. If the model failed everywhere, the path forward would be clear. discard it and build something new, but it fails in one place and succeeds in most others, which means the fix, whatever it turns out to be, must preserve everything the model gets right while changing only what it gets wrong. That is a far more constrained and far more demanding problem than starting from scratch, and the community is working on it from multiple directions simultaneously. The first direction stays entirely within the existing framework and asks whether the astrophysics of the early universe, the messy, complicated physics of gas, stars, black holes, and feedback, was simply more efficient than previously modeled. This is the conservative position, and it has significant support. The argument is straightforward. Pre-Webb simulations were calibrated against observations that did not extend to the earliest epochs with the kind of precision Webb now provides. Those simulations made assumptions about star formation efficiency, about how much gas gets converted into stars per unit time in a given environment, and about how energetically black holes regulate their surroundings. If those assumptions were slightly wrong at high redshift, because the physical conditions in the early universe were different from those at later times, then the models would underpredict the mass, luminosity, and maturity of early galaxies without requiring any modification to the underlying cosmology. This explanation has real traction. Several groups have shown that increasing star formation efficiency by a factor of a few at high redshifts can bring the predicted luminosity functions closer to the observed ones. Others have demonstrated that bursty star formation, episodes of intense stellar production, followed by brief lulls rather than a smooth, continuous rate, can make galaxies appear temporarily brighter than a steady-state model would predict. Because Webb catches galaxies at random moments in their histories, a galaxy observed during a burst phase would look more massive and more luminous than its time average properties would suggest. This does not eliminate the tension entirely, but it softens it. Some of the most extreme objects might simply be galaxies caught at their brightest moment. The bursty star formation idea also helps with the chemical enrichment problem. If stars form in intense bursts, the massive stars in each burst live for only a few million years before dying in supernovae and scattering heavy elements into the surrounding gas. The next burst forms from this freshly enriched material. Rapid cycling between bursts and enrichment events could accelerate the chemical maturity of a galaxy without requiring a longer overall timeline. For the black hole problem, the astrophysical response involves invoking heavier seed masses and more aggressive feeding. Direct collapse black holes, which form from the gravitational implosion of massive primordial gas clouds without passing through a stellar phase, can start at tens of thousands of solar masses, instead of the few hundred solar masses left behind by a dying star. From that elevated starting point, even Eddington limited accretion can reach supermassive scales within the available time. Episodes of super Eddington accretion, where the geometry of the infalling gas allows feeding rates above the classical limit for brief but intense periods, offer an additional acceleration mechanism. Together, heavier seeds and faster feeding can plausibly account for many of the overmassive black holes Webb has found, though the most extreme cases remain difficult to explain without further refinements. The astrophysical approach is appealing because it does not require changing the laws of physics. It requires changing the assumptions about how known physics operates under the specific conditions of the early universe. That is a normal part of scientific progress. Models are refined as new data arrives, parameters are adjusted, understanding deepens. If the entire Webb tension could be resolved by recalibrating the astrophysics of the first billion years, the standard model would emerge scratched but intact, and cosmologists could continue with their existing framework. But there is a persistent discomfort with this resolution, even among those who consider it the most likely outcome. The discomfort comes from the breadth of the adjustments required. It is not one parameter that needs changing. Star formation efficiency needs to go up. Black hole seeds need to be heavier. Feedback needs to be more efficient in some contexts and less efficient in others. Disk settling needs to be faster. Chemical enrichment needs to be accelerated. Quenching needs to happen sooner. Each of these adjustments is individually reasonable, but when you need all of them simultaneously, the question becomes whether you are refining a model or retrofitting it. And retrofitting in science is a warning sign. It means the data is leading the theory rather than the theory predicting the data. That is not fatal to a framework, but it is not a sign of health either. The second direction of response goes further. It asks whether the tension might originate not in the astrophysics of the early universe, but in the cosmology itself, in the fundamental parameters that describe the expansion history, the matter content, and the initial conditions of the cosmos. This is the more radical position, and it is taken seriously by a growing number of researchers. The most developed version of this idea involves a concept called early dark energy, often abbreviated EDE. In the standard lambda CDM model, dark energy is a cosmological constant, a fixed energy density woven into the fabric of space that drives the accelerating expansion of the universe at late times. Its value does not change. It has been the same since the beginning and will remain the same into the future. Early dark energy proposes that in addition to this constant component, there was a second, temporary form of dark energy that was active in the first few 100,000 years after the Big Bang, briefly increasing the expansion rate during the epoch when the cosmic microwave background was being imprinted and then decaying away. The motivation for EDE originally came not from Webb, but from a different tension in cosmology. The Hubble tension, the persistent disagreement between the expansion rate of the universe, measured locally, using nearby supernovae and Cepheid variable stars, and the expansion rate inferred from the cosmic microwave background under the standard model. These two numbers have been in conflict for over a decade, and no amount of improved measurement has made them converge. Early dark energy was proposed as a way to resolve this discrepancy by changing the expansion rate at early times, which shifts the sound horizon, the characteristic scale imprinted in the background radiation, and brings the two measurements into closer agreement. Here is where the connection to Webb becomes significant. A brief period of faster expansion in the early universe does not just affect the background radiation, it affects the growth of structure. A universe that expanded slightly faster for a brief window would have had slightly different conditions for the gravitational collapse of matter. The details depend on the specific EDE model, but in general, the effect is to boost the formation of early structures, producing more massive halos and more luminous galaxies at high redshifts than the standard lambda CDM model predicts. A paper published in 2024 by researchers at the Massachusetts Institute of Technology explored this connection directly. They showed that an early dark energy model that resolves the Hubble tension also naturally predicts a population of bright, massive galaxies at high redshifts that is closer to what Webb observes. The paper described this as a unified solution, a single modification to the cosmological model that addresses two apparently separate tensions simultaneously. This is an elegant idea. It is also speculative. EDE models introduce new parameters that are not constrained by existing data. And the specific form of the early dark energy component, how it turns on, how long it lasts, how it decays, is not uniquely determined by any observation. Different choices for these parameters produce different predictions, and the models have not yet been tested against the full range of Webb data with sufficient rigor to claim confirmation. They are candidates, not conclusions. Other cosmological modifications have been proposed. Some involve changes to the nature of dark matter itself, replacing the simple, cold dark matter particle with something that has additional interactions or decays into other particles over time, altering the growth of structure at early epochs. Others involve modifications to the primordial power spectrum, the statistical description of the initial density fluctuations from which all structure grew, suggesting that the fluctuations may have been slightly different from what the standard model assumes. Still, others propose entirely new physical ingredients, additional fields or forces active only in the first moments of the universe that could boost early structure formation without affecting later epochs. None of these proposals has achieved consensus. Each one resolves some aspects of the Webb tension while introducing new parameters or creating new tensions elsewhere. The field is in a state of active exploration, with multiple competing ideas being tested against the data in real time. This is not confusion. It is the normal process of science responding to genuinely new information. But it is uncomfortable, because the outcome is not yet visible. What can be said with confidence is that the theoretical landscape has changed since Webb began operating. Before Webb, Lambda CDM was not just the leading model, it was effectively the only model that the majority of the community took seriously. The alternatives existed on the margins, discussed at workshops and in specialized journals, but not in the mainstream of cosmological research. Webb has not dethroned Lambda CDM, but it has opened the door to alternatives in a way that the data before Webb never did. The tension is real enough and broad enough that proposals to modify the cosmological framework are now appearing in top-tier journals and being discussed at major conferences without the faint air of eccentricity that once accompanied them. That shift in the sociology of the field is itself a significant event, even if no single alternative model has yet proved superior. There is a third possibility that sits between the astrophysical and cosmological explanations, and it may be the most intellectually honest assessment of where the field actually stands. It is the possibility that both types of adjustment are needed. That the astrophysics of the early universe was more efficient than previously modeled, and that the cosmological framework contains a subtle inaccuracy, perhaps in the initial conditions, perhaps in the expansion history, perhaps in the nature of dark matter, that compounds the astrophysical effects and produces the full range of tensions Webb observes. This compound explanation is harder to test, because it involves multiple moving parts, and disentangling the contribution of astrophysical adjustments from cosmological ones requires data of a kind that does not yet fully exist. But the instruments that will provide that data are not hypothetical. They are either already operating or being built right now. Webb itself is the first and most immediate source of resolution. Its upcoming observing cycles include programs specifically targeting galaxies at the most extreme redshifts, between 12 and 16, corresponding to the first 300 million years after the Big Bang. This is the redshift range where the predictions of standard lambda, CDM, and early dark energy models diverge most sharply. In the standard model, galaxies at these redshifts should be exceedingly rare and faint. In early dark energy models, they should be significantly more numerous and brighter. The difference between these predictions is large enough that even a modest sample of spectroscopically confirmed galaxies at redshift 14 or 15 could begin to distinguish between the two frameworks. The data most likely to break the theoretical deadlock is being collected right now during Webb's current and upcoming observing cycles, using the same instruments that created the tension in the first place. The Nancy Grace Roman Space Telescope, expected to launch in the late 2020s, will bring a fundamentally different capability to the problem. Where Webb sees deep but narrow, Roman will see wide. Its field of view is roughly 100 times larger than Webb's NIRCam, allowing it to survey vast areas of sky in infrared wavelengths. The significance of this for the early universe tension is statistical. Webb's deep fields contain hundreds of early galaxies, enough to establish that the tension exists, but not enough to fully characterize the shape of the early galaxy population across all masses, luminosities, and environments. Roman will catalog early galaxies across sky areas hundreds of times larger, converting what are currently small samples into population-level datasets. With those datasets, astronomers will be able to determine whether the overabundance of massive early galaxies is a universal feature of the cosmos, or whether it varies with environment, whether it is concentrated in dense protocluster regions, or spread uniformly across the sky. That distinction matters enormously for theory, because different explanations for the tension predict different spatial distributions. On the ground, the Square Kilometre Array, a radio telescope being built across sites in Australia and South Africa, will add a dimension that neither Webb nor Roman can access. The SKA will be sensitive to faint radio emission from neutral hydrogen, the raw fuel from which stars form. By mapping the distribution and quantity of neutral hydrogen in the early universe through its redshifted 21 centimeter emission line, the SKA will reveal whether the gas supply available for star formation was distributed differently than models assume. If the early universe contained more gas in the right configurations to collapse efficiently, that would support the astrophysical explanation for the tension. If the gas distribution matches the standard predictions, but galaxies still appear more massive and more mature than expected, the problem shifts more firmly toward the cosmological side. Together, these three instruments, Webb probing deep and early, Roman surveying wide and statistically, and the SKA mapping the invisible gas reservoir, will triangulate the problem from different angles using fundamentally different techniques. The answer is within reach. It is simply not here yet. And this is where the meaning of the title becomes clear. James Webb made the early universe look wrong again. Not wrong in the sense that everything we know is false, not wrong in the sense that cosmology has collapsed into chaos, wrong in the sense that the version of the early universe that lived comfortably in the scientific imagination, the version that was simple, primitive, slowly assembling, safely predictable, has been shown repeatedly to be less stable than everyone thought. Each new data release from Webb adds another observation that does not quite fit the comfortable picture. Each new confirmation tightens the tension by a small amount, and the word again is the most important word in the title, because it points to the pattern rather than any single discovery. If Webb had found one galaxy that was too massive, the community would have noted it as an outlier and moved on. If it had found one black hole that was too heavy, the same response would have followed. Anomalies are expected. Science is built to absorb them. What science is less comfortable absorbing is a persistent, directional, multi-axis discrepancy that appears in every dataset, at every epoch Webb examines, across every observable property the telescope can measure. That is not an anomaly. That is a signal. And the signal says that the early universe was more than the comfortable story prepared us for. The emotional dimension of this shift deserves acknowledgement, not because science is supposed to be emotional, but because the people doing the science are human beings who spent their careers building and testing a model that now requires significant revision in one of its most foundational predictions. The hierarchical model of structure formation was not just a technical framework. It was a narrative. It told a story about how the cosmos went from featureless simplicity to the rich, structured, teeming universe we inhabit. That story had a beginning, a middle, and an implied ending. It had a pace. It had a logic. It felt right in the way that a good story always feels right, each step following naturally from the one before it. Webb has not destroyed that story, but it has made the early chapters harder to read with the same confidence. The beginning is no longer as simple as it seemed. The transition from simplicity to complexity is no longer as gradual as the models predicted. The cosmos did not wait patiently for billions of years before building anything interesting. It built mature, structured, chemically enriched, dynamically organized systems within the first billion years. And it did so across a wider range of environments and evolutionary pathways than anyone anticipated. This is not a crisis in the dramatic sense. It is something quieter and, in its own way, more profound. It is the slow realization that the universe's earliest visible epoch, the place where the origin story is supposed to be at its simplest and most transparent, is in fact one of the least understood eras in all of cosmic history. The more Webb reveals, the more complex the picture becomes. And the complexity is not random noise that will eventually average out. It is structured, directional, and persistent. It keeps pointing in the same direction every time the telescope opens its instruments and looks backward. The most unsettling aspect of this situation is not any individual observation. It is the consistency of the pattern. Massive galaxies too early. Overmassive black holes too early. Quench galaxies too early. Spiral structure too early. Stellar bars too early. Protoclusters too early. Chemical enrichment too early. Dynamical maturity too early. Non-rotating dead galaxies too early. Each of these findings was published by a different team, using different data, analyzing different objects at different distances. They were not looking for a pattern. They were answering individual questions about individual systems, and yet the answers kept landing in the same place. Too mature, too developed, too far along, too fast. When independent lines of evidence converge on the same conclusion without being designed to do so, the conclusion gains a weight that no single observation can carry. The convergence is the finding. The pattern is the discovery. And the pattern says that the early universe resists the simple version of its own story. There is a way of thinking about this that does not require panic or revolution. The standard model of cosmology is a map. For decades, it was the best map anyone had ever drawn, and it guided the field with remarkable success across nearly every region of the cosmos it was applied to. Webb has now explored a region that the map covered only in broad theoretical strokes, the first billion years. and what it found there does not match the cartography. The landscape is more varied, more developed, more richly featured than the map indicated. That does not mean the map is useless. It means the map was drawn confidently before the territory was fully explored. The correction that is needed may turn out to be modest, a few contours redrawn, a few elevations adjusted. Or it may turn out to be significant, requiring new features that the original cartographers did not anticipate. Either way, the map will be better afterward. That is how science works. Observation exposes the limits of existing understanding, and the understanding adapts. But adaptation takes time. And during the period between the recognition that the map is incomplete and the completion of a better one, the field exists in a state of productive discomfort. That is where cosmology is right now. Productive discomfort. The data is ahead of the theory. The observations are more detailed, more numerous, and more consistent than the models can currently explain. And the telescope that created this discomfort is still operating, still observing, still collecting data that will either resolve the tension or deepen it further. Webb's primary mission lifetime was designed for a minimum of 5 years, with fuel reserves that could extend operations to 20 years or more. As of now, the telescope is healthy, its instruments are performing at or above specifications, and its observing programs continue to target the most distant and earliest objects accessible from its position at L2. Every month brings new data. Every cycle adds the statistical weight of the early universe samples. The surveys grow deeper. The spectroscopic confirmations accumulate. And with each edition, the picture of the early cosmos becomes a little sharper and a little harder to reconcile with the version that existed before the telescope launched. The early universe is not broken. Cosmology is not in ruins. The Big Bang still happened. The cosmic microwave background still tells us what the universe looked like at 380,000 years. Dark matter still provides the gravitational framework for structure formation. Dark energy still drives the accelerating expansion. The broad outlines of the cosmic story remain intact. But the early chapters of that story, the ones that describe how the first structures emerged from the primordial fog, how galaxies assembled, how black holes grew, how the cosmos transitioned from featureless simplicity to the richly structured place we observe today, those chapters are being rewritten, not erased, rewritten. The new version is more complex, more dynamic, and less comfortable than the old one. It describes a universe that did not wait, a cosmos that built mature structures in what should have been its infancy, an origin that resists the clean, patient, hierarchical narrative that 3 decades of simulation and observation had made feel inevitable. James Webb made the early universe look wrong again, not because the telescope found one impossible thing, but because it keeps finding, with every new observation, that the earliest visible cosmos is more developed, more structured, and more mature than the familiar version of the story comfortably allows. The discomfort is not that we know nothing. The discomfort is that the universe keeps pushing back against the simplest version of its own beginning, and the more we look, the less simple the beginning appears. That is not a failure of science. It is science working exactly as it should, driven forward by a telescope that refuses to show us what we expected to see. The comfortable story held for decades because the instruments that preceded Webb could not see deeply enough to challenge it. Now an instrument can. And what it reveals is a cosmos that started faster, matured sooner, and organized itself more thoroughly than anyone predicted. The old beginning was a story we told ourselves because it was the only one the data supported. The new beginning is the one the universe is telling us, whether we were ready for it or not. The telescope is still watching. The data is still arriving. And the early universe, it turns out, is still not finished surprising us.